Welcome to the first video on stochastic differential equations with Lipschitz continuous coefficients. All right. So in the last video, we introduced the notion of stochastic differential equation and studied the case of linear ones. And now come to chapter 5.2, where we want to consider the more general class of stochastic differential equations and study the existence and uniqueness of a solution to these differential equations. Right, so what we want to consider is, as before, the dynamics of our stochastic process X is given by coefficient mu, which determines the drift of the dynamics, and volatility function sigma, which is the diffusion part. So this is somehow the fluctuation of the equation. And at time 0, we start from some deterministic point x0. This is over the interval 0 to t. All right, so this is to be consistent with the lecture notes equation for 5.4. And what we have seen is if we have linear stochastic differential equations of mu and sigma are affine function, then we can always write down an explicit solution. But in general, this is not true. And one needs numerical methods to simulate or approximate the solutions. But at least if the coefficient are uniformly Lipschitz continuous in the solution process X, then one can derive an existence and uniqueness result for this solution. And this is the main goal of this section, which is Theorem 5.3, which is about the existence and uniqueness. So uniqueness is, we haven't discussed uniqueness of a solution at all. So, but if you have it for Lipschitz continuous one, we can conclude it for the affine case as well. Okay, now I need to give you all the ingredients. So what we want is that mu and sigma, well, they are functions from the time interval 0 to t and r. So right, we have a real value process to r. Be two measurable functions. But this is not enough regularity to ensure the existence of a solution and uniqueness. And we want that they satisfy for some constant c, we have then 0. We want that, okay, mu xt yt, so right, this is, and sigma minus t, right, can be estimated uniformly in the time. So we have a constant, and then we estimate it by difference of x and y squared, right? So this is just saying it's Lipschitz continuous. All right, and now we want to have a second condition, which is a linear growth condition, which says, okay, if I look at mu absolute value and sigma and absolute value, right, then I can estimate it again uniformly in time, the constant in 1 plus x squared. Right, and this holds for all t in the time interval 0 to t and x and y in r. Okay, and okay, what one last thing. Okay, and what we also want is, okay, our initial condition x0 is in r. Okay, so this is our setting. So we have a linear growth condition and a Lipschitz, uniform Lipschitz condition in the solution. Okay. So what is now the statement of the theorem? So this is the setting. And then we have following three things. So first, there exists a solution xt dt of the SDE 5.4. Right? So 5.4 is just the general stochastic differential equation which we started with. All right. So we have always a solution. Every solution xt is uniformly bounded in L2. What does it mean? If you look at the supremum over the whole time interval 0 to t, then the L2 norm, so the supremum of all the L2 norms here of the process x at time t is finite. Okay. And the last part of the theorem is actually we have uniqueness in the sense that, okay, so solution x dx of 5 is pathwise unique. Again, what does it mean? Well, for any other solution y, which also solves our equation 5.2, so our SDE, we have that it's indistinguishable to x. So this means if you look at the event that for all t, the process x is equal to y, then this is an event of probability 1. Okay, so this is the claim. So, well, the statement. So if we have Lipschitz continuous coefficients uniformly in t with respect to the component where we put in the solution process, and we have a linear growth condition, and then we have a unique solution to this equation. And we also know that this solution is uniformly bounded in L2, which is just a bonus. All right, so let me give you a remark before starting to prove it. Right. The first thing is, well, the Lipschitz condition is as, or like, as in the case of ordinary differential equations. Right? So if you have learned about ordinary differential equation, you will remember that, okay, if you set sigma to 0, you have an ordinary differential equation. Then if you know you have Lipschitz continuous vector field here of coefficient mu, you have your Picard-Lindelöf theorem, which guarantees you the existence of a unique solution. And the proof was based in a Picard iteration. This is exactly what we are going to implement in order to show its uniqueness here as well, existence here as well. All right, and then you had the linear growth condition. So the linear growth condition on essentially guarantees a global solution, right? Because otherwise we could have a blow up of the solution. So that a global here just means that we can solve it up to the terminal time, capital T, which was given, right? For example, let us consider the following little deterministic example. So what we do is let's set sigma to be 0 and look at the equation 1 over beta minus 1 of x to the power beta dt. And we start this system by 1. Right? This is an ordinary differential equation. And we want to assume that, okay, x is positive. So that beta is strictly bigger than 1. Okay. In this case, well, this is a simple equation which we can solve. And the solution x is just given by 1 minus t to the power minus 1 divided by beta minus 1. Right? Indeed, let's check this is a solution. Right? So it's not hard, right? We just have to check it. So calculate it. So let's take the derivative of xt defined like this here. So we have 1 over minus, right? We have 1 over 2, right? Then we take here minus t minus b beta 1 minus 1. And here we go. Right, we can rewrite this exponent to be minus beta divided by beta minus 1. This is nothing else than 1 over beta minus beta at t, right? And this is what we claimed here. But in particular, this means this solution blows up if t gets bigger than 1, right? Because if you look at this solution, I mean, you have a singularity at 0, at 1, so we cannot keep solving this equation. If capital T gets bigger than 1. So the solution x has no extension. Right. The point being, okay, we really need to have the linear growth condition in order to ensure that we can solve the equation on the whole time term. All right. So in this video, I'm only going to prove uniqueness, and in the next one, then I'm proving the existence. In order to prove uniqueness, we need, as actually for ordinary differential equations, we need Cronville's lemma or inequality. This is 5.5. And okay, yeah, I'm giving you the simple, very simple version, which it's sufficient enough. First, I'm just giving you the Cronville's lemma because it hopefully was part of some other lecture, but still, if you want to see the proof, you can find in the appendix of the lecture notes, you can find the proof of Cronville's lemma. But here, let me just give it to you. So we take a function g, which is bounded and measurable. And then the statement is if there are two constants, so constant a, b, and r, such that I can estimate g by the constant a plus b times the integral from 0 to t of g. Then Cronville is telling me that I can estimate actually g, the function itself, by a times the exponential of b times t. And the good thing is, if a is 0, then we know that our function is less than 0, or if it's a non-negative function a priori, we know it's equal to 0. Okay. So proof is that can be found in appendix 8.5. Okay, so I'm not going to do it here, but if you're interested, please check it out. All right, so let's proof of theorem 5.3, which is this is the last step, right? So we assume we have existence, we have the uniform bound. We start with this simple, this simple uniqueness. Right? It's always the same idea. So if you have uniqueness, you suppose you have two solutions, right? Suppose y and x are solutions of the SDE 5.4, or this is just our ST. Okay. Now we want to show that they're identical, right? So what you first thing you observe, if I look at the difference of x and y, well, what is it? Okay, the initial value, they cancel out because they have the same initial value. Then I have the integral here, mu minus, also evaluated at x and then evaluated at y. Right? And well, I get the same, or the linear operator, integrals are linear operators, so we get here sigma x sigma s, and then an integral with respect to the Brownian motion. Okay. And this means, well, okay, if I look now at the L2 norm of the difference, I want to show actually, if I know that this is 0, then I can conclude that the processes are the same. Okay. What? So I want to use this equality here. Plus, right, this, I mean, we have seen the move. This again here. So if I have a plus b squared, I can estimate from above by twice a squared and twice b squared. All right. So let's use this. So I get a 2 times the integral, also the expected value of the integral. Right. Oh. Here we go. ds, then everything to the power 2. And okay, I missed. Okay, I have the same from the stochastic integral. Right? So twice the expected value of here we go, the stochastic integral. Oh, that's a y. All right. And so here, okay, let me try it. Right, in order to save some time. So what do I have here? Used here, I used Ito's isometry. Right. All right. Oh, okay. Okay, let me give you the next. Okay, now let me give you an extra line. All right, this is. So let me move it out here. Sec. All right, this is. I mean, I will use e to the trigonometry, but I give you an extra line. All right. So, okay, I want to use them and move this term in here. For the first one, I need to use the Jensen's inequality. So, yeah. It's inequality. Right, so the length of the interval comes in front, and then I have the expected value of the integral. Here we go. Square s, right? And now I use, for the second term, I use e to the isometry as I promised you to do. All right. Here we go. And this is kind of gray by e to the isometry. All right. And now I use the Lipschitz continuity, and this is, I mean, I can estimate these terms here inside of the integral. So what do I get is, okay, 1 plus t, right? This is the vector from here and here. And then I have a constant c, which comes from my Lipschitz bound, and I have here the expected value, the integral from 0 to t of the difference of xs minus xy. Right? So, okay. Lipschitz condition. All right. Okay. Okay, this looks good, because now let us define, we introduce the function g, which is nothing else than this here. So we introduce it, it's the expected value of the difference of x and y to the power 2. So the L2, almost the L2 norm. So the L2 norm to the power 2. Right. So if we have this, okay, what does this mean? I mean, this is just, so I just labeled here the right-hand side to be g. So I know from these estimates that gt is less or equal. I mean, gt is actually a function which is non-negative. It's less or equal than twice. And then let me lose capital T, right? The small t can be estimated by capital T plus 1. And then I have c, and then I have the integral using Fubini of this, right? Okay, that's great, because this is exactly what Cronville is telling me, right? If I have such an integral estimate, I can estimate, use Cronville, and here my a is 0, as I hoped for, so I know that g has to be less or equal than 0. And since g is positive, I know g has to be positive. Okay, and this is bounded, right? We know that g is bounded. G is bounded by property EEII of the theorem. All right, hence Cronville lemma yields that G is identical to 0. All right, cool. Okay. So what does it mean? Almost surely, I mean, okay, we have a probability 1 that x is equal to d for all t and t, and by continuity, and this was part of the definition, continuous, we know that for all t, x equal to y has the probability 1, which is the pathwise uniqueness we wanted to show. And we're done. All right. So thank you for watching the video.